So, what we're going to talk about today. Actually, I'm hoping these next couple of days can help us coast into the exam, because there's stuff we've talked about, but it's in a more general setting than we've done before. So I don't think it'll be too much of a big leap. We're just going from our end to maybe perhaps a more general setting. And today, what we're going to talk about is vector space. Now, I think this is kind of something that we're a little bit used to, but I don't want to over trivialize it. I'm going to give you some stuff today, some theorems that might show up, either in applied or maybe asking you some questions, the short answer questions on exam. So when I hear dimension, we've used this kind of intuitively, but what do you think? What's the number that what's the dimension number we associate to a vector space? What is that coupled with? Right. So if I say a vector space is 5-dimensional, what does that mean?
All the way over in R5.
Well, just because it's in R5 doesn't mean it has to be 5-dimensional. It means it can be less than or equal to 5-dimensional. And it doesn't necessarily have to be R5. It could be some other wacky, midnight gospel kind of 5-dimensional vector space, right? So the dimension comes from this right here. The dimension of a vector space is the number of vectors in any basis. So when you talk about dimension, what you're talking about is how big is the basis, right? And what is a basis? It's a linearly independent spanning set, right? It's the most economical way to write the elements of the vector space. The dimension is just giving you sort of an idea of size of it. A 1-dimensional vector space, well, that's just multiples of one vector, non-zero vector. A 0-dimensional vector space has no basis whatsoever, and that's just the 0 vector. Right? A 2-dimensional vector space, like the plane, to describe any vector in there, you take 2 parameters, right? 3-dimensional and so forth. So let me start off with our first theorem. By the way, this number could also be infinity as well. Infinity is not a number, but you can also have vector spaces of infinite dimension. And we'll look at that in a moment. Let V be a vector space with basis so suppose I've got a vector space with basis V1 up to Vn. Of course, this means this is an n-dimensional vector space. Then any set of n plus 1 or more vectors in V is linearly dependent. So if you pick more vectors than is the dimension of the space, that automatically has to be a linearly dependent set. So if you are living in a 5-dimensional vector space and you pick 6 vectors, 7 vectors, 10 vectors, automatically it's linearly dependent. And I am going to go through this one. I'm going to show you why this is true, because it illustrates some stuff that Jared talked about when you all last met. Um, so this is actually going to use some stuff. So this is really kind of more of a computation. Suppose we have K vectors, V1, V2, Vk, with K bigger than N. So what I've done is I've picked a bunch of vectors, pick them, and I picked more vectors than is the dimension of the space. I claim that these vectors have to be linearly dependent. Now, how do we show this? Consider now the vectors V1, V, V2, V, K. These are vectors in Rn. And these are the coordinate vectors of V1. Y'all remember the coordinate vectors, because basically what do we have here? What happens to V1? V1 in this vector space. So let me kind of give you kind of a quick example. I'll stop this here. For example, V1, whatever it is, it's a linear combination of this. Everybody agree? Because this is a basis. So I could write this as C1, V1. V1 can be written as a linear combination of V's. And these are the coordinates or the weights that you need. Everybody agree with that? And so V1B, this thing right here, is just this n vector that I make out of these points. Everybody okay with it? I think Jared talked about these border vectors last time. Yes, sir.
Why you have these and then it's a B in?
Again, it's the magic markers thing. You're absolutely right. There we go. Is that better?
Yeah.
All right. Okay, everybody with me so far? So this right here, these are all vectors in Rn, right? So I claim that in Rn, these vectors are linearly dependent. And can somebody tell me why? This one is kind of, yeah, go ahead.
You have more columns and rows on that paper.
That's exactly right, right? These are columns, right? And the columns are all n tall, right? So I've got n rows. So if I were to put this in a matrix, right, I would have an n by k matrix. Everybody agree with that? And if it's an N by K matrix, I've got more columns than rows, right? Is it possible for me to have for every column be a pivot column? No, because I've got more columns than I got rows, right? Not all columns. If I make the matrix by these things here, P1, B, up to D, K, B. And so, this collection of vectors here in Rn have to be linearly, or I'm sorry, linearly dependent. So, we can find AI, bunch of numbers, with A1, B1B, plus A2, B2, B, plus AK, BK, equals 0, with not all because these vectors, and these are vectors in Rn, are linearly dependent, I can find some numbers that are not all 0 that make that equal to 0, right? Well, so how does this work for us? Uh, well, actually, this is 1-1. Last time you had this coordinate mapping where you go from your vector in your n-dimensional space into Rn is 1-1, and in fact it's onto as well. So this starts in my V, which is an n-dimensional space. It ends up in Rn. This is 1-1 and onto. And it is a linear transformation. It's also onto, but 1-1 is all that I need here. So A1, B1 plus AK, BK, because this is a linear transformation, this is equal to A1, B1 plus A2, B2 plus AK, BK. That is, this thing right here is a linear transformation, so I can do it all at once, right? Because the linear transformation, I can put the constants inside and then put all the sums inside and I get this. And this is 0. Emphasis. But since this linear transformation is 1-1, since this association is 1-1, this means that this must be 0. Why is this 0? Because I know that any linear transformation takes 0 to 0. And since it's 1-1, that's the only thing that it can take to 0. So this mass goes to 0. This has to be 0 because it's 1-1. And so, since not all AIs are 0, this set is linearly. This theorem is a small observation, but it's going to help. So here's the moral of the story. If you have any vector space of dimension n, if you pick any set of vectors that exceeds that dimension, it's got to be linearly dependent. This will be useful to us shortly. Any questions on that? Okay, here's kind of the first application, yes. Here. I really probably should put this theorem first because, this gets me to the definition of dimension. As a matter of fact, theorem, if V is a vector space, and we'll say if it has a basis of n elements, so what I call a dimension, then every basis of the as n elements. Let me say exactly, sort of emphasize it. So this may lay some fears to rest. You might have a vector space that has a basis over here that's got 5 elements. Maybe I might think that over here I've got some other basis that's got 7 elements. This is impossible. If you have a basis that's got 5 elements in it, any basis of that vector space, and there'll be infinitely many of them. Any basis of that vector space will have 5 elements. And this sort of justifies, this gives the fact that our definition of dimension is well defined. Why is that? Well, let's say, suppose B and C are both bases. Well, if I can write this out for B1, Bn, and C equals C1, CK are both bases. So suppose I've got a basis of n things, and I've got a basis for k things. How do I know that n and k have to be the same thing? That's the previous theorem. So that's right. So no, if k is greater than or equal to n, or I'm sorry, strictly greater, then C is linearly dependent. Everybody agree with that? That's what the previous theorem said. I've got a basis of n things. If this is bigger than my basis of n things, it has to be linearly dependent. Agreed? So this can't be bigger than n, right? And by the same token, this is a basis. So if n is less than k, if n is greater than k, then B is linearly dependent. Right? Because this is a basis, so this can't be bigger than this, right? So that can't happen, and that can't happen. What choice am I left with? They have to be. This is kind of a cool theorem because it puts to rest the worry that I might have had about my definition. Maybe I have bases of different sizes. Impossible. All bases of a vector space have to be the same size. This is also true for infinite dimensional vector spaces as well. Okay, any questions? So let me expand on my definition of, just for clarity, of dimension in the following sense. If these vector space, then number one, if V consists only of the zero vector. So V is the smallest vector space that we ever imagine. Then dimension of V is equal to 0. We say it's got a basis of 0 elements. The empty set. There's logical reasons for this. Let me point out that the only possible basis for V would be the 0 vector. But the 0 vector can't be a basis for 0. Anybody tell me why? The 0 vector is always linearly dependent, so it doesn't work. So we say that the vector space consisting only of the 0 vector has dimension 0. Then dimension of V, then. So your next case is if it's not the 0 vector, it might have a basis that only consists of 5 things. And 3, if V has no finite basis, then sometimes we say the dimension V is infinite. Further distinctions can be made on the size of infinity, but that's probably beyond the scope of what we want to talk about here. Can anybody give me an example of well, okay, so I'll start with this. Anybody give me an example of a finite dimensional vector space?
One.
Yeah, that didn't work actually, because your vector space has to have 0 in it.
Oh, yeah, I guess it makes sense.
So, yeah, that's right. So how about 0? That works, right? 0 is a 0-dimensional vector space, right? What's your favorite n-dimensional vector space?
All these are.
Okay, right, spanned by that, right? Rn, right, that's the favorite one. That's kind of one we were born and raised on in a certain sense, right? The Rn. How about and there are many bases, but I'll write a basis down here. E1, E2, E. That's my favorite, most convenient basis. Can anybody name another n-dimensional vector space? Maybe you've seen a few times.
Yeah.
How about this one? All polynomials of degree n and less, and the 0 polynomial front end. What happens when you add 2 polynomials of degree n and less? You get polynomial of degree n and less, 0. When you multiply that by a real number, you get another polynomial of degree n or less, right? What's the dimension of this? That could go good. Thought I'd trick you, but I didn't. Degree n plus 1. Right, the basis here, my favorite basis. And if you count them, you've got sort of one extra because you start counting it x to the 0 power, right? That's why it's in this. Everybody okay with me? Okay, how about, can somebody give me an infinite dimensional vector space? One that has no finite basis, but it's a vector space nonetheless. right? Okay, yeah, actually, you're right. That was like on total steroids, right? Let me pull it back a little bit and I'll come to your example. How about this one? Yeah. No restriction on K other than it's got to be greater than or equal to zero, right? So these are polynomials, not just of some degree or smaller, but any size you want, right? By the way, let me point something out. This may be a subtlety. All polynomials are finite sums, right? Because every polynomial has a biggest degree, right? Even though this is a infinite dimensional vector space, can somebody explain to me why it's an infinite dimensional vector space? Why is there no finite basis for this?
Okay.
Right. Let's suppose that you had a finite basis, right? Just for giggles. This finite basis is all polynomials. List them. P1, P2, all the way up to P, say K, right? And suppose you've listed them in increasing order of degree, right? So the largest degree polynomial you have in your so-called basis is, say, of degree, I don't know, J, right? All you have to do is look at x to the J plus 1, and there's no way you're ever going to get that by writing a linear combination of smaller polynomials, right? So it's not possible to span this with a finite set. Everybody agree with that? Can somebody name me a good basis of this? What do you suppose my favorite basis of this is?
Would have to be, 1x and all the way up to xk, right?
Yes, let me, I'm not picking on you too much. It doesn't have to be, but actually that's probably the smartest. Just don't stop. Right? Any polynomial that you ever could want is a linear combination, but I need infinitely many things because no matter what degree bound I set, you might pick something high, right? You might want to start at the millionth power, billionth power, whatever. But every polynomial, is it clear that every polynomial is a finite linear combination of these, right? And it's also fairly easy to check these are linearly independent, right? What does it mean for an infinite set to be linearly independent? It means that if you have a finite sum of these, right, times constants, that all the constants have to be zero. So another way to think of this is an infinite set is linearly dependent if it has a finite linearly dependent subset. Linearly independent if not, right? So if there's no finite linearly dependent subset, it's linearly independent. Does everybody see this example here, the infinite dimensional vector space? And there's a lot of them. You threw it, you said, what did you say, continuous functions, right? So this one right here, C. This is an old calculus problem. What happens when you add two continuous functions, you get a continuous function. What happens when you multiply a continuous function by a number? Continuous function, all right? So this is a vector space. Let me point out, all polynomials are continuous, right? So this is a subspace of this, right? And it's a tiny subspace of this because sine x is not here. Neither is e to the x, neither is the absolute value of x. I don't even know where to start to write a basis of this, right? It is death on a hot plate, but there it is. It's a big vector space, right? Everybody look at that. Much bigger even than this. Okay. Any questions on that? Okay, here's another example. Here's kind of something I wanted to interpret geometrically. Think about geometrically. How about subspaces of what subspaces of R2 look like? There's one of them, right? Just the zero vector. Yawn. What are the, can somebody describe what the one-dimensional subspaces look like? Absolutely, yes. Can you be a little more specific? Not just any old line. It has to go through the origin. It can even be vertical, but one-dimensionals look like this. There's a one-dimensional. Of course, they have to go through the origin because any vector space has to have the zero in it. I think it's vertical line. Notice that there is a boatload of subspaces, right? All three of these green lines are separate one-dimensional subspaces. Right? Okay. How many two-dimensional subspaces are there? Just the plane itself, right? Because once you have two linearly independent vectors like these two, everything in the plane is a linear combination. Right? In fact, I know a basis for all of R2, E1 and E2. That's size 2. So if you throw two linearly independent vectors in there, by what we've seen already in class today, that'll generate all of that. That'll span all of the plane. Right? How about three-dimensional space? Well, you got that crazy point again, right? There's your zero dimension. But now you've got, in the one dimensional, you've got all kinds of lines and all kinds of, I should draw up, shouldn't I? And all kinds of wacky directions. What do the two-dimensional ones look like? What are the two-dimensional subspaces of this look like? Yeah, right. They're planes again. They have to go through the origin, right? But so, for example, any kind of yeah, that's most of them are prettier than that. But anyway, any plane that goes to the origin would be a subspace. How many three-dimensional subspaces are there? Just R3 itself, right? Because once you have the three vectors, you've got everything. But think about this. If you have four-dimensional space, just like there are infinitely many planes that you can kind of twist around in three-dimensional space, there are infinitely many different three-dimensional subspaces in four-dimensional space, which is, crazy to try to picture. Okay. Questions? All right, so here's a theorem I alluded to before, and I'm going to show you why this is true on the Jackson basis theorem. This is actually a very important theorem. Yes. Well, actually, what W and V be a subspace? Then any linearly independent subset of W is contained in, or another way to put it is can be extended to a basis for that. And what is more, the dimension of W is less than or equal to the dimension. So if you imagine this, here's W, and we'll say in some larger vector space V. If you have a linearly independent set in W, so it's linearly independent, right? You need two things for a basis. You need a basis to be linearly independent and span, right? Here's the content of this theorem. If you have a couple of a set of linearly independent elements, either they're a basis already, or you can sprinkle in a couple more vectors, maybe a few more, and expand it to a basis, right? So that's what it says. If you have any linearly independent subset of W, then that linearly independent subset, if you can grow it to a basis, it's contained in some larger basis. And the dimension of the subspace is less than or equal to the dimension of the parent space, right? Which we would hope to be true. Now, why is this true? This is an incredibly important theorem because it allows you to start with the seed. The seed can be, in fact, I can tell you, for example, in Rn, suppose you have a vector space. How do you start the seed? Just pick any vector that's not zero by itself. It'll be linearly independent, right? Because if you have a vector by itself, it's not zero. The only way to get zero by multiplying it is to multiply by zero. So if I start with one linearly independent vector, that is one non-zero vector, then I can grow it to a basis. And actually, this is something in the we're going to do later called the Graham-Schmidt process that allows you to build convenient bases in certain settings. So why is this true? Well, let me go through this. If W equals zero, then nothing. Because W doesn't contain any linearly independent subsets, right? And the dimension of W is zero, which is certainly less than because vector spaces do not have negative dimensions, so I've got that way, right? So let's assume that W is not zero. If it's not the zero vector, we'll let S be a linearly independent set. Actually, a linearly independent subset. Okay. So let's suppose we have this linearly independent subset. If now, so I was sort of given this linearly independent subset here. It turns out if this linearly independent subset spans W, then I'm done because it's a basis. It's linearly independent W and it spans. What if not? I mean, that could be the only shortcoming of my linearly independent subset is if it doesn't span it. What does it mean to not span W? It means there's something left over. Everybody agree with that? So when I look at all the linear combinations of all the junk I've got in S, there's something in W left over. Agree? If not, select any, we'll call it WK plus 1 in W that is not in the span of S. And I claim that this set I now claim that I can take this new thing that was in W but wasn't spanned by the other ones and throw it in there, and it's a bigger linear set. Can somebody explain why that's true? Why would that be true?
Well, the span is the set of all of the linearly dependent vectors. So if you take something that isn't in that span, then that extra vector has to be linearly independent as well. Which means it's all
Yeah,
set
you know,
is still linear.
that's kind of the idea here. Let me go with the first one. Suppose C1, W1, C2, W2, CK, WK, CK plus 1, K plus 1 is equal to 0. We can assume okay, I'm gonna make this off plane. I can assume this one is not 0. Why is that? What happens if this is 0?
Well, it would already be in the original span.
That is correct. If this is 0, then now I've got a linear combination of the WI is equal to 0, and that means that all these have to be 0. Because W1 and WK was linearly in the first place, right? So the only way this could ever be interesting is if this is not 0. Everybody agree with me? And so, what does that mean? Take that over to the other side, and I get, or take everything else over to the other side. How about that? CK is not, CK plus 1 is not 0, right? Right, we can divide by it. And tell me, what does this mean? What is this equation? The equation should speak to you like the voices to me. What's this equation telling? This thing is in the span of the other ones. Everybody agree? WK plus 1 is in the span of W1 or WK. Plus 1 is the span of W1 of the WK, which is impossible. Because we selected WK plus 1 not in the span of S. That means that it must have been linearly independent. So a new set is linearly independent. Now, are we going to have to go through much more? No, because what we've shown is we have a linearly independent set. If it spans W, then if it doesn't span W, we pick something left over from the span, right? That's not coming about put in there. And now we get a new linearly independent set. Agree? If this spans all of W, we're done. What if not?
Yeah.
You do this process again. Now, the thing that bothers me, especially for some of you computer science people, is how do I know this process is going to terminate? I don't know, or it has to terminate. It's like fun. That is right. The dimension, if the dimension of W is n, then this must stop. For n on or before that. Because any set in an individual, if you have n plus one elements, they're automatically linear.
So you can stop with it having n elements, just not exceeding.
Yeah, that's right. Yeah, it has to, it can get all the way up to n, but it can't go any farther than dimension because any n plus one elements are linearly dependent. So this process has to terminate. And so at some point, we will get this. And from this, it follows that the dimension of W is bounded above by the dimension of the vector space, V, the parent space as well. Everybody understand how that works? Yes, sir.
What if n is infinity?
Oh, that's a great question. But it turns out you can't prove it this way if n is infinity. But you have to use some other fancy matter. But that's a great question. This is true, the theorem is true as well for infinite dimensional. If you have any linearly independent subset of any vector space, you can expand it to a basis. But you can't, I can't demonstrate it to you this way. Let me give you this last theorem. This is called basis theorem. And this follows from what we've been doing today, and hopefully this would kind of be a rehash. Here. Let B be, yeah, okay. Let B be a vector space. And dimension of B. And I want my vector space to be of dimension at least one, so I don't want to share anything. Zero vector space here. One, any linear independent subset of V within elements. Yeah, a basis. See? So if you know, so notice this theorem a priori tells you that you know at the outset this is an n-dimensional vector space. If you go find in an n-dimensional vector space n any linearly independent set that has precisely n elements in it, basis, automatic. And number two, any spanning set. That is a collection of vectors that span V with exactly n elements. Is a basis. So if at the outset you know that you have an n-dimensional vector space, if you collect any n elements that are linearly independent, basis. If you collect any n elements that span the space, basis. And that's all you have to know if you know the vector spaces of dimension n. Okay, any questions? Any questions on that? I will probably post your next quiz will be Friday at 8 o'clock, probably this afternoon.
What kind of quiz